So hello everyone. So I'm a PhD student at the Weizmann Institute, and I'm going to discuss today my work, the work that we've been doing in the past 4 years. Indeed, it is related to the non-thermal emission that follows compact objects merger. It is based on 3 papers and 2 more that will become public in the coming weeks. So let's begin. So when I'm discussing compact objects merger, I basically mean binary neutron star mergers and black hole neutron star mergers, because the electromagnetic signal is related to the ejection of mass from such objects. When they become close enough, around megakilometers, they're going to lose energy due to gravitational waves, and then eventually they're going to merge. There are a few potential electromagnetic transits that are related with such mergers. It can be GRBs, Kilonova, and the non-thermal afterglow I'm going to discuss here. GW170817 provided a great example for such an object. It has rich phenomenology, both in thermal emission, we've seen the Kilonova, and non-thermal emission, we've seen gamma ray emission, and we've seen the afterglow from a relativistic outflow. Okay. So when you have a compact objects merger, you expect relativistic mass to be ejected in 2 distinct possibilities. There's a mild relativistic outflow, basically the Kilonova ejecta fast tail, that is geometry is similar to spherical, it's quasi-spherical. It can reach 60 to 70% of the speed of light, at least from what we observe from binary neutron star merger simulations. And it is denoted here in blue. In red, you can see a relativistic outflow that is ejected from the poles. The ejection mechanism is much more complicated. It reaches much higher Lorentz factors, and its geometry is, as you can see, very different from spherical. So these 2 distinguished components will provide 2 different types of electromagnetic signal if we're considering the synchrotron emission. But the mechanism is basically the same. You have this outflow propagates into the interstellar medium, a collisionless shock is being created, it propagates and accelerates electrons to relativistic velocities. With the magnetic fields that are also being created, it's going to emit synchrotron radiation. So basically the main difference is the properties of these 2 outflows and not the mechanism. So let's go over the properties. The mild relativistic ejecta has masses of around between 10% of solar mass to much less than that, while the highly relativistic mass is much lower in mass, but higher in Lorentz factor. The geometry, as I mentioned, is quite different, and the mild relativistic outflow, the peak time of the synchrotron signal that we expect to see is much longer than your typical highly relativistic outflow peak time scale. This is because of the higher mass and the lower Lorentz factor. It takes time to decelerate such a
Sorry, Gilad, this claim that you have 10% of solar mass or so in a mildly relativistic outflow, you mentioned that it is based on a simulation. Did many groups confirm the same result? How reliable are those simulations?
Yes, many groups and many different simulations, and we did observe 5% of solar mass ejection in GW17.
Oh, it even has some almost direct confirmation.
Yeah. Okay. Good. The ejection mechanism of this mild relativistic outflow can be from shocks due to the collision between the 2 neutron stars. It can be related to the tidal forces the object with the higher mass extracts on the lower mass object, and there could be winds from the disk, but this is even a more complicated case. Anyhow, let's make some order and explain what I'm going to talk about. I'll begin with discussing this mild relativistic outflow, the potential signal. We provide analytical and semi-analytic descriptions of the signal. It gives us the parameter and the generacies, the parameter dependence and the generacies. We'll validate our results with full numerical computations. It will provide us with reliable inference of parameters from future observations. And eventually, we're going to discuss how we expected to see such a signal from GW170817. Now, as I said, the peak time scale is around 10 years. Not enough time passed since GW170817. But should we keep observing it in the coming years? And then I'll discuss the highly relativistic outflow signal. Discuss the existing modeling for the signal that we did observe from GW170817, an alternative approach that we're suggesting these days, and a simple model for the synchrotron break frequencies that will be important in the coming years as we expect to see more and more outflows which are observed off-axis. Okay, eventually. So what we do observe in simulations, right? So basically what you see here is a cumulative plot of the ejected mass in simulation for Gilad et al. 21. It's the mass above a certain gamma beta as a function of this gamma beta. There are a few trends we should notice here. First of all, that below gamma beta of 0.1, which is around 10% of the speed of light, there's almost no additional mass. All of the mass is being ejected in higher velocities. When you go to velocities which are higher than 10% of the speed of
Sorry, I
light.
have no idea what you are talking about. So this plot, mass versus gamma, it's what is the result of numerical simulation of those people, not of you.
No.
This is what the people who merge like Shapiro, who merge neutron stars,
Indeed.
they predict that such mass is ejected with such velocity.
Indeed, and this different coloring is for different mass ratio between the two neutron stars and different equation of state for the nuclear meter. Okay, so this is what we see in simulations. It is repeated for different groups and different simulations. This is just one example. When you go to velocities which are higher than 10% of the speed of light, you see a trend which is like a moderate decline in your profile, and then after some arbitrary cutoff, there's a steep decline as expected. So we notice that we can express or span all of these parameter space, all of these possibilities with a simple broken power formula.
What is the escape velocity from the surface of a neutron?
Around 30% of the speed of light.
So we should not be surprised that we are getting 0.1 or whatever. It's roughly the escape velocity, so the material.
Yeah, exactly, it is expected.
Sorry for interrupting.
Okay, it's fine. One thing you should notice is that when you go to higher velocities, as the mass fraction is extremely low compared to the mass in the simulation, we're talking about neutron stars, so around one solar mass, the energy conservation for such a low fraction of the mass is very difficult to do, and there are significant deviations between different results. So a model that actually can explain what would be the ejecta properties from future observations is essential. Okay, so we notice that we can express most of the properties of most of these results with a simple broken power formula. It's denoted there in black. So the mass above a certain gamma beta can be just a simple broken power function, and we gave the typical parameters that can span all of the parameter space. So we can use this formula in order to say something about the observations and the ejecta properties, but we need to actually calculate the synchrotron signal from such an outflow. So we used basic afterglow modeling, which means we assume fraction of energy held by electrons in bimagnetic fields, and we assume the electrons follow a power distribution. This is typical modeling for all the GRB afterglow we observe. As the outflow propagates into the interstellar medium, the shock collects more and more shocked mass. So you might be expecting your light curve to rise because you keep having more and more electrons. Problem is you also decelerate because the reverse shock is propagating into a ejecta. So the deceleration it decreases the internal energy density, which means you might be expecting a decrease in your light curve. So it's not really clear, should you expect a rise and then a decline or only a decline? We'll get there. So the solutions that were
should be initially a rise, because initially you have zero.
Right, but should be like on a time scale of what time scale should we actually observe this rise? Previous modeling that tried to say something about this signal were using extrapolation from the ultra-relativistic regime or the non-relativistic regime and provided simple expressions. The problem with this is that there is a very large dependency for the peak flux at the Lorentz factor. So this extrapolation can be very risky. It allows you to provide simple expressions because you can just take gamma goes to 1 or beta goes to 1 and get a simple solution. So we did some work and I was able to create simple expressions without these extrapolations. We'll show it in a second. Why is this important? Because if we were able to use modeling of the synchrotron signal in order to constrain the properties of the ejecta, we might be able to say something about the binary system parameters, the equation of state of nuclear matter, or even the merger dynamics. So we began by producing analytic and semi-analytic descriptions that are based on the approximate solution of the dynamics. The analytic gives us simple expressions for the parameter dependence and the degeneracies between different parameters. And the semi-analytic solution provides us with an ability to extend our solution to a non-spherical geometry. Eventually, there are assumptions here, so we have to run full numeric computational simulations in order to validate our results. The disadvantage, obviously, from such a working method is that it demands a lot of computer resources. The simulation can take up to 2 days, so you can't spend all of your parameter space this way. Obviously, you need to integrate over the emissivity and all of the cells in your simulations, and properly take into account the relativistic effects and the arrival time of the radiation. Bottom line, the analytic and semi-analytic models that we produce are in very good agreement with the full numerical computation. We'll see. Okay, so let's discuss some key analytic results. As I said, it is not clear whether we should have a rise or for how long we should have a rise. So the answer is that as long as the reverse shock propagates through the steep part of the ejecta, we said there's a steep part for the ejecta at higher velocities and a more moderate part of the ejecta at lower velocities. So as the reverse shock propagates through the steep part of the ejecta, we expect our light curve to rise. This is because the deceleration is not very efficient as the reverse shock propagates through the steep part. Imagine your reverse shock.
Sorry, could you just sort of like draw a sketch? I think I'm getting confused about where the different parts are, like the reverse shock.
Yeah, let's say you have this is your profile and it propagates into the.
No, I mean a physical. Oh, okay, sorry. I understand. That's true. And so that was the stuff that's blasting off the neutron star.
Yeah, it was ejected. It can be ejected due to tidal forces or due to the shocks.
Yes.
Okay?
But that's the density profile as a function of distance.
This is basically the mass profile, but it's similar. The density profile looks kind of similar.
Oh, of course.
Okay. Anyhow, so as the
I think what Lennis is asking, there is a lot of high mass moving with small velocity, but on top of it there is little mass moving with high velocity. That's what this graph is showing.
Yeah, exactly. So as the reverse shock propagates through this steep part of the ejecta, let's say it got here at some point. Now, in order to decelerate the next layer, which is much more massive because of this steep profile, you need to collect a lot of interstellar medium mass. So the deceleration is not very efficient as long as the reverse shock propagates to the steep part of the ejecta.
You know, I'm very ashamed that I don't understand this better. But I would have thought you can't have a reverse shock until something's already gotten there.
Yeah, the reverse shock is propagating, let's say the reverse shock is propagating through the steep part of the ejecta.
And it was initiated by this very small amount of mass that was traveling faster.
Yeah, indeed. So as it propagates, you need to decelerate the next part of the ejecta, the next layer which is much more massive. Okay, so you need to collect enough interstellar medium mass in order to do it. But if the next layer is much more massive, it will take you a lot of time in order to do it. So as the reverse shock propagates through the steep part of the ejecta, the deceleration is not very efficient, and the effect that wins is the fact that you keep on collecting a lot of interstellar medium mass, and you have a rise in your light curve. When you get to the moderate part of the ejecta, exactly at this break, your light curve peaks, and then you start to decline, because the deceleration is much more efficient. Eventually, the reverse shock crosses the whole ejecta, and you get to a non-relativistic flow that is well approximated by the set of Taylor solution, and you get a different temporal dependency in your light curve. Okay. So these are the model parameters, the mass profile, the parameters that are related to the mass profile, the density of the interstellar medium, fraction of energy held by electrons and by magnetic fields, the parameters of the electrons, and the distance.
So you're moving into a uniform ISM?
Yeah.
Okay. Nothing comes from the progenitor?
Nothing comes from the progenitor, only a uniform ISM. We're talking about distances which are extremely large. We're talking about 10 to the 16 to 10 to the 18.
Because progenitors are neutron stars, right? Merging neutron stars, so only ISM is around.
Well, there was something else before there were neutron stars,
Oh, that's long gone.
Okay.
Gone.
Right, because it's a binary neutron star merger. Very
right.
fucking sorry, very slow.
Okay, so we have analytic expressions for the flux temporal dependence, for the peak flux and the peak time, as you can see like that. We have a simple expression for the angular size of this thing on the sky. Imagine something which is moving in tens of percent of the speed of light for 10 years. It will be large enough in order for us to resolve it. So typical size around 10 milliards seconds. So we need an analytic formula for the angular size of the sky. And for the synchrotron break frequencies, There's a lot of analytic formula, so such that for a well-observed event, if we'll be able to observe all of these observables, we'll be able to reduce all of them on the parameters. Okay. Let's see some examples. So here on the right-hand side, you can see two light curves produced by our full numerical computation in the dashed lines, and our full analytic solution in solid lines. There's a very good agreement between the two. In order to actually do the full numerical computation, I had to write a 1D relativistic hydro code along with the proper radiation calculation in order to actually calculate the light curve. So the light curves are in very good agreement. This here is a snapshot of the intensity map on the sky. So as you can see, it looks like a narrow ring. This is due to relativistic effects. So if you had a sphere that emitted photons in some initial time t0 at some viewing angle, and as it expanded relativistically, it kept on emitting more photons, but now they were emitted they also emitted on axis. Eventually they will arrive with photons that were emitted in a larger viewing angle an earlier time. So
what's the significance of the blue and the orange?
Just internal energy density. As it expands, it decelerates and cools.
So this is simultaneously showing us that, and
No, this is an earlier time. The red one is an earlier time, and the blue one is after it got expanded. Okay, so maybe I'll explain it again.
I thought you said this was something somebody would observe at a particular time.
At this one, that's the map you would observe.
Misunderstood what you're
Now I'm
referring to.
explaining why would you see it as a narrow ring. So the explanation is at some initial time you emitted photons, you emitted radiation in various angles. Let's look at specific this angle with the red arrows. So I emitted radiation at some specific viewing angle, and then the sphere or the shock expanded. The internal energy decreased, but you keep on emitting radiation also on axis. These two photons will arrive to you at the same time, but one of them was emitted for a much larger internal energy density. So you would see it as a narrow ring on the sky. This happens only because the expansion is relativistic. It can compete with the velocity of the radiation. Okay, so we have the point is we have an analytic model for the ring radius on the sky. You can see it here in the solid line compared to the full numerical computation in dashed line. So there's a very good agreement. We have another analytic formula we can use in the future. Good. How does it compare with the earlier results I discussed? So there's a significant improvement. We can see on the right-hand side an example for, again, another light curve. Dashed line is our full numerical computation, solid line our analytic modeling, and as you can see, the previous modeling there in dotted line misses the peak flux by an order of magnitude. This can be significant if you want to reliably infer parameters from future observations. It goes the same for the self-absorption frequency, and for example, we have here the peak time ratio of the previous formula over our formula. As you can see, there's a factor of few difference, and it becomes worse when you go to larger velocities. So it's important to use the accurate formulas in future observations. Let's continue. So far I was discussing the spherical ejecta. It well approximates the ejection from compact objects with the same mass, with the mass ratio that is close to 1. When you have a mass ratio which is more significant, let's say above 1.5, then most of the ejection is due to tidal forces. Now, when you eject mass through tidal forces mechanism, it means that one of the massive objects tears apart the less massive one, and all of the mass that is within the orbital plane and just break through the escape velocity can escape away within the orbital plane. So what you see in major simulations of both binary neutron stars with high mass ratio and black hole neutron star major simulation is that all of the mass is being ejected within 20 degrees from the orbital plane.
But this GW was equal masses, no?
So it's currently we don't really know the bounds from the GW itself lies between 1 to 2.
When you say GW, you mean 11780?
Yeah, we win 117. So if you don't assume something about the speed,
I'm just totally ignorant about neutron star binaries. Is it a realistic case, 1.5 ratio? I thought all neutron stars roughly have mass 1.4. Am I mistaken?
They are, but there are solutions that we did observe neutron stars which has mass of 2.
So it is
No, but in the binaries, they're very consistent. They're not, there's not
we
a big
only
spectrum.
observed one binary system.
No, but if we see
No, there are lots
pulsar
of
binaries.
binaries.
Yeah, we see the pulsar binaries, and there they have a very small
1.4,
dispersion.
right?
the total mass is consistent to within 5%. And the
Okay,
pulsar
but
binaries, and then individual masses, I don't think there's much more.
it is yet biased to pulsars in our galaxy, so we don't really know. It might be possible for
There's
2
something
neutron
like
stars.
38 of them, so how can they be
I
terribly
don't know.
biased?
I don't know. It could be. But anyhow, this is more relevant for black hole neutron star systems.
Okay, that we can buy, okay.
I thought the drawing makes the.
Oh, okay.
Anyhow, so you have
I'm
this black hole.
confused. Some of the pictures, I have the idea that you're looking down, and other ones you're looking kind of at an angle. Could you just tell us what the observer looking from the
This is not a
same?
simulation. This is just a drawing of a
Yeah, that's
black hole.
right, but are we supposed to be always looking at the same perspective, or are they 3-4 different perspectives?
It's just a drawing to give you an indication of how come the mass is being ejected only in the orbital plane. That's it. It doesn't have any physical significance. Okay, so as I said, in merger simulations of both black hole neutron star mergers and neutron star mergers with a high mass ratio that we don't know exist but let's say we hypothesize this possibility. The mass is being ejected within 20 degrees from the orbital plane, and we cannot approximate it with this spherical idealized solution. Okay, we have already 3 confirmed neutron star black hole mergers that we see in GW, and currently the fraction of such system which has a significant mass ejection is tens of percent. So we expect to see such ejected profile, such ejected masses in the coming future. Okay.
Sorry, can you say it again? We have seen already 3 neutron star black hole mergers in gravitational waves?
Yeah.
But none had an electromagnetic counterpart.
No, not an early one. But this time scale for this type of signal is around 10 years.
Or you are saying there is still hope?
Yeah. Okay, so how do we approximate such an ejecta? We use a toroidal shape. Basically, it's a sphere truncated by a double-sided cone. The lateral expansion is negligible. This is due to the fact that as the reverse shock propagates, you keep on injecting momentum in the radial direction. So the lateral expansion is negligible, but you had to make sure it does happen. So we had to run full 2D numerical computations to check it. We used RedFNA. It's a 2D relativistic code, AMR code that has been developed in the Weizmann Institute 10 years ago. We had to modify it and improve it for our purposes, but okay, so it works, and you can see 2 examples here. So this is a snapshot of the mass density of such toroidal ejecta. Indeed, the lateral expansion is quite negligible. This is a snapshot of the Lorentz factor.
Is that a log scale, or I can't
Yeah,
read
it is a log scale of the mass density.
So give us an idea what the numbers are.
So the typical densities can vary, depends on the distance you're looking at. Okay, so typically here the mass density of the medium is around 10 to the minus 23, and the mass density of the ejecta itself can reach 10 to the minus 20, 10 to the minus 90.
Grams per centimeter cubed.
Grams per centimeter. Okay. So this is what we did. We found out our semi-analytic description can actually approximate quite well the 2D relativistic computations. So when we we concluded 2 very interesting results. Let's begin with the left-hand side. So this is an example for light curves from our semi-analytic computation. This is a toroidal ejecta observed in different viewing angles. Okay, when I'm saying different viewing angles, so 0 viewing angles means that the on-axis line of sight is perpendicular to our orbital plane, and 90 degrees means that the line of sight is parallel to the orbital plane. So this is 0 degrees and 90 degrees. Obviously, we expect our outflow to be brighter at 90 degrees. This you can see here in purple. Anyhow, what we noticed, which is maybe not that surprising, is that the peak flux and the peak time doesn't really depend on the viewing angle. It doesn't really change, although it is still relativistic, and relativistic beaming does have a little effect. The peak flux is not very sensitive to the viewing angle, and the peak time also. And we have a simple analytic formula approximating the peak flux and the peak time there in black plus. How does it compare with the spherical ejecta solution? You can see it in black up there. Obviously, the spherical ejecta has larger mass. We expect it to be brighter, and indeed it is brighter. But the only parameter that actually differentiates between the peak flux in this case and in this case is the amount of mass in the fast tail, not all of the geometric stuff.
But this is because the Lorentz factor is low, right?
Yes.
Yeah.
The Lorentz factor here, the cutoff is around 30% of the speed of light. Yeah, it's a 1.05 Lorentz. Okay, another point, although the peak flux doesn't really change significantly, the intensity map on the sky really changes. You can see it here on the right-hand side. So this is 4 snapshots of these calculations. So the different viewing angle really changes the intensity map on the sky, and the size of this thing, as I mentioned earlier, at the distance of 100 megaparsec, is 10 milliarcseconds on the sky, which means it can be resolved. So using the intensity map in the future, we might be able to say something about the ejecta geometry and the viewing angle.
And in fact, it was resolved for this GW.
No? In GW17, it's a different case. We'll get there in coming.
But it was resolved, no?
It wasn't resolved. It is just we can observe the motion of the sky, but we can't.
Or
we
it
can
was,
resolve
okay,
the,
centroid motion was all resolved.
Yeah. The blue line there is our estimation for the ring radius in the spherical case. So it gives us an estimation what is the typical size of this.
I don't understand 10 milliarc seconds? Isn't this like a parsec?
This is just this is a simulation with a specific set of parameters that were used in order for us to run the simulation fast. But if you use realistic parameters, the size of this thing is around 10 milliarc seconds.
Okay. So
But for some distance.
so much big. So it's like must be much bigger than a parsec,
Yeah,
right? Because then it's 100.
I said tens of percent of the speed of light
Yeah.
that goes around for 10 years. It's a lot.
Just, what is it?
Well, that's not even a parsec.
Why not?
Because
Because
it's a
10
light
years
year.
is 3
It's a light
parsec.
year. It's less than a parsec.
10 years is 3 parsec, right? If it goes slower, then it is a parsec. So it is a parsec at what? At 100 megaparsec, the distance to this stupid thing.
So it's 10 to the minus 8.
Huh?
It's 10 to the minus 8.
Right.
Parallax.
Milliarc seconds.
Yeah.
10 to minus 8, which is kind of
Milliarc.
milliarc second.
Okay.
It's okay.
Okay. Got it.
Oh, we can compute, huh, Mike?
Yeah.
Okay. So about GW170817, the observations we have are due to a relativistic component ejected from the poles. You can see it here in blue and turquoise. It's not what I discussed so far. We'll get there in the coming slides. What I was discussing is the potential signal for the mildly relativistic ejector. We draw potential results from given the bounds we know from the Kilonova ejecta about. So the Kilonova ejecta gives us some bounds over this mildly relativistic potential mass. We use these bounds, and we also assume some parameters for epsilon E and epsilon B, the fraction of energy held by electrons and by magnetic fields, and we can produce potential light curves that can be observed in the coming future. So as you can see, the peak time of this potential signal is more than 10,000 days, around 30 years. That's a lot. But it might become observable after something like 10 years. It can reach the sensitivity limit of Chandra and the VLA. Okay. At the peak, due to the close proximity of GW170817, the size of this thing on the sky is 45 milliarc seconds. So it certainly will be resolvable by the VLA.
But sorry, but still I come back to what Mike was saying. So for this 45 milliarc seconds, you do need, in fact, ultra-relativistic flow, no? Because if it is just mildly relativistic, let's say 0.3 speed of light, then there are no time delay effects, no funny business with superluminal motion, right? Then in 10 years at 0.3 speed of light, you will be at 1 parsec.
This specifically peaks after more than 30 years.
30 years, 3 parsec. 3 parsec at 100 megaparsec is 3 times 10 to minus 8,
Yeah.
which is,
No, that works out. It works out.
Is it
right?
okay?
Yeah, I think so. You said it before. Yeah, I think it's right.
Yeah, it's fine.
it's okay.
100% sure it's fine.
All right, go ahead.
Yeah, I was miscalculating in my head when I was expressing alarm before.
Okay, so this is it for the mildly relativistic potential signal, which should see in the future if it is relevant. And
I did have a question about this though,
Yeah.
which is there's an assumption about the density of the medium that matters, right? That sets this time scale somehow. What is that assumption?
So here specifically it's 10 to the minus 3 centimeters.
Okay.
Mach to the minus 3.
Particles per cubic
Yeah,
centimeter.
particles per cubic centimeter. it is consistent with the bounds we know from GW17 about the density.
And it's like an elliptical galaxy, so it's like
the
some
outskirts of
more-
an elliptical galaxy, so it's a very low density.
Yeah, okay.
Okay. So let's go to the actual observations of the highly relativistic component ejected from the poles from GW17 or 17. So what we see here is the observations from radio to X-ray. All of them are normalized to 3 gigahertz with a synchrotron spectrum. So they would sit on the same light curve. We see a shallow rise in the light curve, but then a steep decline. It peaks after 150 days approximately. These results are from many authors. Macatini was 21 was gathered all of them together for this nice curve. We also have a very unique observation in level 17 and 17 of the centroid motion on the sky. We can see a superluminal motion. It means the location of the object on the sky changed in a velocity which is larger than the speed of light. It means basically there's a relativistic component that propagates toward us in some viewing angle which is not negligible. So we have the localization from Hubble Space Telescope 8 days after the merger, and then we have localization from the high sensitivity array 75 and 230 days after the merger, and another location from the VLBI 206 days after the merger. Basically, if you just use a simple analytic point source approximation, you get around the Lorentz factor of 5 in order to create this kind of motion, and the viewing angle which is between 15 to 30 degrees. So this is the bulk parameter space we should look at. Okay, so typically when you try to model this stuff, specifically in GRBs, you usually use a top hat jet model, which means you have a very narrow core of ultra-relativistic matter with very high Lorentz factor. And its energy angular profile is constant, so you have like a section of blend from the key solution, which propagates into the interstellar medium. Now, since we know that in GW17 we have a significant viewing angle, we should consider what would happen if we observe such an object in some viewing angle. The problem is with this solution is that the rise would be much too steep in order for it to be consistent with GW17 observations. In there, the shallow rise went like t to the power of 0.8, while in this typical solution the rise goes like t to the power of 3. So this solution can't explain GW17 or 17 for sure. Okay. So what did people do? Okay, so instead of just taking this top hat ultra-relativistic solution, we can add an energy angular profile to this very narrow core. This energy angular profile goes like some free function of theta. It can be Gaussian, it can be a power law. But now, when you observe it off axis, there's a shallow rise due to the fact that you keep on observing angular sections that were initially hidden due to relativistic beaming. So you keep on, as it accelerates, you keep on looking inside into angular sections which were further away from you, and the rise is moderated this way. So you can explain the rise with this kind of modeling. There is kind of a challenge trying to explain the decline, because when you have full relativistic solutions, full relativistic calculation of such an outflow, the typical decline you observe is much steeper than the minus 1.9 you observe in GW17 or 17. So that's a first challenge. The second challenge is it's hard, there are no full numerical computations that were able to actually calculate both the light curve and the centroid motion and provide a solution that gives solution that fits both of them, at least with full numerical computations of hydrodynamics. Okay, so on the right-hand side is what is usually considered. We suggest a different approach. We suggest a conical stratified outflow. It means we have a wide angle with a lower Lorentz factor outflow that propagates into the interstellar medium, and it's stratified as before. It means we have a lower mass with higher Lorentz factors at the front, and higher mass with lower Lorentz factor lower Lorentz factor at the back, and it propagates into the interstellar medium. Again, there's a
So say it again. So you are saying like McFadyen and others, they were considering
This is the
pure BMK.
No, the pure BMK within this.
Right. So it was some structure in angle, but no structure in radius.
Yeah, the BM
BMK structure in radius, and you are taking different radial structure.
Indeed.
We
The
Andrew, that you consider pure BMK?
What does
In
BMK
radius.
stand for?
Blandford
Blandford
McKay.
McKay.
Oh, okay.
We have a different model, it's called a boosted fireball, which gives an angular structure from throwing a fast hot cloud.
But did you have this funny radial structure, like stratified, high Lorentz factor in front, lower behind?
No, it forms BMK
Okay.
after it sweeps outside.
Yeah, this is what typically considered, and it fits when you keep on fitting the parameters. You can fit the light curve, but it's hard fitting both the light curve and the centroid motion. And there's a slight problem if you want to fit the decline. I'm not sure if we can make it work with some tweaking, but this is the situation at the moment. So we consider this solution a wide angle, stratified structure. The shallow Y is due to the fact you keep on converting kinetic energy from the inner layers into the internal energy of the blast wave. So you have a shallow rise, and due to the wider angle and the low Lorentz factor, the decline is much more moderate than the steep narrow curve. Okay, so again, we had to actually do full 2D computations in order to model such a thing. So this is an example for a snapshot from the simulation. This is the mass density. So as you can see, in black you can see the initial opening angle of our structure. We have high density within the initial opening angle, such that the lateral expansion is negligible, at least as long as the reverse shock propagates through this outflow. And you can see also the shock front here as it propagates into the interstellar medium. So we used our semi-analytic modeling to see if it fits with the full 2D computations. You can see it here on the left-hand side. This is one example. The light curve also are consistent. This is an example for the center of light motion of such an object on the sky. In dashed line, there's the semi-analytic calculation, and in solid line, you can see the full 2D computation, which are consistent with each other for different parameters and different viewing angles. Now, we used our semi-analytic modeling in order to fit GW17 or 17 observations, and then we ran full 2D numerical computation to actually validate these results and get the light curve after the peak and at the central motion at late times. And this is how it looks like. Okay, on the right-hand side, you have the centroid motion, the observations in yellow from GW17 or 17, and our full numerical computation that fits the data. On the left-hand side, you can see the light curve you've seen before with our full simulation that fits the data almost perfectly, just a slight deviation here at the decline. Okay, so it's good. We have the first single component full numerical computation that is based on full 2D hydrodynamics that fits the data. It's a good thing. It means we can fit GW17, but it means that maybe there's a larger degeneracy between different structures that can fit the data with completely different outflows. Okay. For example, this outflow has quite a wide angle. It's an angle of 10 degrees, which is very different from the typical angles usually considered for GW17 and 17. So maybe it says something about the fact that we can't really resolve the angle. It's an open question. Okay. Last slide about an analytic model for the break frequencies. So when we studied this thing, we noticed that GW17 has a very unique property that you don't see the Coulomb frequency or the minimal the peak synchrotron frequency. It means that all of the observations from radio to X-ray lies in a single part of the synchrotron spectrum. Okay. We want to actually do some calculation and understand what does it tell us about the interstellar medium density, about the Lorentz factor of the outflow. So we've seen that at the literature, the formula for the break frequencies are only for ultra-relativistic outflow that propagates on axis. But for GW17 or 17, it is certainly not the case. We have shock plasma of around Lorentz factor of 5 that propagates off axis. So we had to extend the formula for the literature. For example, this is for the peak synchrotron frequency and for the Coulomb frequency. So they will include the effect of viewing angle which is larger than 0 and lower Lorentz factors. For example, we applied this formula to GW17 and we got the following bounds. The ISM density times the fraction of internal energy held by magnetic fields is smaller than 3 times 10 to the minus 7, which is an extremely low number.
Sorry, what's epsilon B?
The fraction of energy held by magnetic fields out of the blast wave internal energy. And the Lorentz factor of the shocked plasma that contributes to the emission lies between 2.6 and 12 all throughout the emission. Okay, so these bounds were not considered before, at least for DWC.
Do we know actual density of the interstellar medium and the location of this event?
We don't know. We have some X-ray observations of the surroundings, which gives you lower densities around 10 to the minus 3. But this is also provides with a very low number for the factor
For
of energy.
epsilon
held by
B,
the-
right? This
which
is
very-
exactly
which
what
is
I
very
was asking.
not trivial.
So N is kind of measured to be 10 to minus 3.
It can be, I'd say, between 10 to the minus 4 to a few times 10 to the minus 3.
Okay, but in any case, this epsilon B parameter must be very small.
Yeah.
So only a tiny fraction. Even though for these GRBs, they are often small, right? Epsilon Bs.
Usually it's between 10 to the minus 3, 10 to the minus 2.
Okay.
But this is even lower than that.
What epoch would that be, though? Like, if you think of this Kiyuchi et al. Simulation, in the early, like, first second, it's epsilon B is 1.
Well, the simulations that actually, you're talking about the simulations that actually do calculating the measure and the ejected metal form.
And the formation of the jet.
So epsilon B can change significantly. We're talking about
So you're
completely
talking
different
about-
time scales, completely different
Right,
densities.
exactly. So I wanted to ask you what time, this is this sort of 1 year type time scale.
So it begins to be right after 10 days. You see it in
I wanted to ask,
value after
is
10
this,
days.
you speak as though epsilon B is just a fixed number, but presumably it's evolving.
Yeah,
I wanna
obviously
know-
I'm talking about only after it went to a significant distance from the merger site. We're talking about distance of 10, above 10 to the 15 centimeters. Okay.
And then after that, you think it's okay to think of it as a fixed number?
It is well modeled with GRB afterglows. You can see it doesn't significantly change a lot. There's a paper that actually calculates what would be the effect of epsilon B that changes not drastically, and the effect is very minor.
This is a big puzzle, right? What is this epsilon, right? Because it's magnetic field created by the shock wave itself. God knows. This is mystery.
Indeed. We show here that the previous formula for the ultra-relativistic on-axis emission for the cooling frequency, for example, divided by our new formula. So in red line, you can see what happened with emission on-axis. When you go to higher Lorentz factor, they coincide. The ratio goes to 1 in red there. But when you go to lower Lorentz factors and different viewing angles, for example, 4, 8, 12, you can see there's a factor of few deviations. So if you want to actually infer bounds from this kind of formula, for future observations that will, most of them will be observed off-axis just by statistics, you need to use this formula. Okay, let's conclude. So we derived analytic and semi-analytic descriptions of the synchrotron emission of the mildly relativistic ejecta. They will be essential for reducing models from future observations, model parameters from future observations. They are supported by 1D and 2D adaptive measure fine relativistic hydrodynamic calculations, and they are accurate to tens of percent, which is a significant improvement over the earlier results we had.
Are we expecting a lot of this double neutron star mergers?
So the rate was should be few in a year. The last run that didn't find anything maybe made it a bit lower, but I know that the expectation for the next LIGO run is a few.
Per year?
Yeah. But we didn't observe yet one since GW17 on 17.
Well, they think they have a second one.
They have claims
Okay,
about
it
the second
depends
one,
on
which is very
assuming it's not
distant,
a
and
right.
it's not completely confirmed. We have a result regarding the viewing angle, which doesn't significantly affect the peak time and the peak flux, but it does significantly affect the angular intensity map on the sky, which can be used, and because it can be resolved. Good. Regarding the second part, we provided an alternative for the observations of GW17 or 17, the non-thermal observations. We suggest a wide-angle, radially stratified outflow with a lower Lorentz factor. It accounts for all of the non-thermal emission properties, both the light curve and the centroid motion. I didn't mention it in the slide, but there's a significant difference with the behavior of the light curve for different viewing angles, which means in the typical structured jet we consider usually in the literature, the on-axis emission from such a component would show only a decline in the light curve, while in our modeling, on-axis emission will provide a rise in the light curve. So it is a significant difference, so it can be tested in the future. We also derived analytic expressions for the synchrotron break frequencies, which are valid for lower Lorentz factors and different viewing angles, which will be essential for future observation in order if you want to interpret the properties of the parameters of future observations. Okay, thank you very much.
Questions? Then I last one. What is this, what about this 30 years or whatever? Like we had a talk here recently by one of our grad students. He was predicting like in 5 years when he is about to look for a professorship, there will be a peak, which is exactly what he predicts. So what about you? Are you predicting a peak in 30 years or whatever?
Look, first of all, it's
No, I'm semi-serious actually, right? Because for me, this is the only test of whether or not we actually know something, if you can successfully predict not the past but the future. So can you predict? Are you saying that this GW in 10 years will become bright?
I completely agree. I think there's a very good possibility that we're going to see a rebrightening in the light curve. Obviously, it depends.
Because of this non-relativistic part of the...
Yeah.
And sorry, am I right to think about it as if kind of like a supernova remnant will become visible, so to speak, in some sense? Right, because
it's much more relativistic, right? It's much more relativistic, so
than the usual supernova remnant.
And you should notice here that the peak light curve is only a few, factor of few higher than the peak sensitivity. So maybe, I don't know, maybe the sensitivity will become much better in the coming 10 years. But you can slightly change the parameters and you won't be able to see it.
But we should see it in radio or what?
In radio and in X-ray.
Oh, also in X-ray?
Yeah.
In both?
Yeah.
In 10 years?
Let's just hope
More than 10 years.
Let's hope we have an X-ray satellite out there at that point.
10 to 4. Oh, it's, what is this?
10
It's
to
30 years.
Yeah.
Oh, that's long.
That's long and it might be too weak for us to observe. So I wouldn't say for sure I'm expecting us to observe it, but there's a good possibility and we should monitor.
And in fact, that part of the analysis is kind of reliable, right? Because the non-relativistic part of ejecta is what people do see in almost direct numerical simulations, right?
Yes, and we can see that the Kilonova ejecta itself reaches the velocity of 30% of the speed of light. Obviously, by definition, there has to be a faster tail that is slightly in front of it. So there has to be some kind of a structure like this, but it's highly dependent on the parameters if you'll be able to observe it or not. And you know, we can slightly change epsilon v there, and that's it. And since epsilon v is such a mystery, we can't really say for sure. Yeah.
I have a question about something you didn't directly speak about, but presumably the mildly relativistic component is the component that will have done the R process work originally.
Mm-hmm.
And I just wondered, is there conceivably any imprint of that in all of this story? Like, how
So
do one imagine?
the part in which you expect all of the nucleuses all of the radioactive decaying stuff that's going to happen is the moderate part of the ejecta. So in this part of the ejecta, between 10 to 30% of the speed of light, you expect at least what we've seen from the Kilonova that we did observe. You expect this is the place in which these radioactive activities are going to happen. This thing has an imprint on the light curve after the peak. Okay, so the slope of this thing is a parameter in our modeling, and it does affect the decline of the light curve just after the peak. So we might be able to say something about the profile, the mass profile of the structure of the mass profile of this moderate part of the ejecta. So we might be able to say something about the ejecta structure, velocity structure after the peak. Yeah, but as I said, the peak time is extremely long, so we won't be able to say something anytime soon.
But by modeling Kilonova, we kind of do know that 1% of solar mass has been ejected with 10% the speed of light?
5%.
Huh?
5% of
5% of, like this was seen
Yeah.
almost directly.
Yeah.
Because kilonovas we can compute, kind of.
I wouldn't say we can compute, but
Okay.
so if we can't actually calculate the radiation transfer in a supernova and kilonova, it's much more complicated. Yeah, it's a different.
Can I ask a philosophical question? So what? So we do understand almost perfectly all those explosions. Why should I care?
First of all, we don't really understand all of the physics of neutron stars. So we don't really know how come they are found in binary systems. We don't know the nature of the nuclear matter behavior within them. So this type of understanding the properties of the ejected material would help us to understand, one, stuff about the binary system. How come they are found in binary system? What happens is, are these two massive stars that went to supernova? Is some kind of a different process? Two, we don't really understand the mass ejection mechanism. We don't really know. The simulation provides us with many possibilities.
But I thought you said they see it in numerical simulation.
Yeah, we do see mass ejection, but we see many options, and as you can see, there's a very large uncertainty between the different simulations. We need a model to be able to say something
okay.
about. If we want to actually reliably say something about the structure, we'll have to use observations. So this is the way to use observations in the future.
Should we?
Bob, is there a bow shock produced by Mars?
Yeah.
Because Mars doesn't have magnetic fields, right?
I know, but.
But as a solid